back at it with u substitution, and I'm going to do g and h at the bottom. So we're still doing indefinite integrals. There's no a and b. That's the second part of today. We'll then do some, well, what if there's numbers there, and we're going to do definite integrals. Now, cosine squared x, I'm on g. If you look at the top of your page, cosine cubed x we did last time. Now, with these, the first thing you should try and do is look for the composition and see if that would work. For example, this really means cosine of x squared. So then there would be a composition, cosine and then some function squared. That's 2 and 1. So try out u being the inside, which is just cosine x. It's not x, it's not cosine x squared, that'd be too much. The inside part is cosine x. Now, if we do the derivative, remember this, you got to get the derivative on the outside. The derivative would be negative sine x dx. And there's no sine x out there, and there's no way for us to create that. So this doesn't work. You can cross it off, or you can just erase. I'd say cross it off, because like that's the first attempt you should do. So then, do you remember what up here in E? Yeah, actually, so remember in D it worked. When we let u be sine of x inside, that worked. In E, we separated it, we changed it somehow. And then it did work. So that's what I'm going to do here in G. Now, real quick, if I changed it from the above trig identity to 1 minus sine squared, right? We did that in E above. If I did that, well, there would be a composition, the sine x and then something squared. So I could let u be sine x. But the derivative is cosine. There is no cosine up there. So that one won't work. So what I can resort to, though, is a different trig identity. And what I'm going to do here is an identity right here for cosine squared x. Okay, I put the double angle ones on the right there as well, sine 2x. Sometimes can be useful. But if I change it to this, it's going to actually work for us. So before I even write the u, let me change this using this identity. So it's going to be equivalent to 1/2 parentheses 1 plus cosine 2x, and then dx. Now, there's different ways to kind of go about working this out. I'm going to distribute the half. This is what I'm going to choose to do. It's kind of different ways, what if you want to do with the half. So I'm going to distribute the half. It's 1/2 plus 1/2 cosine 2x dx. Now I'm going to do the sum rule. Before I even do, I'm going to need a little u substitution. First I'm going to do the sum rule. Right? It says I can do each integral separately. So the one on the left I can do. Right? The integral of 1/2 with respect to x is just 1/2 x, right? The integral of a number is just number x. So it's just 1/2 x. We keep going. Plus the integral. Now this one I will need to do something else. So I'm going to write 1/2 cosine 2x dx. Okay, for this one, the second half of that integral, I go back. Do I know an antiderivative for cosine of 2x? No. Because cosine x, that'd be good. But what I can do is use substitution. Now there is an inside, right? I didn't put parentheses there, I can. But the inside is 2x. Right? 2x and cosine together, that's the composition. So I will let u be 2x. This will work, so you can write it u equals 2x.
Oh my god, I get it.
So then we always do the derivative. U prime, or I write du, the derivative with respect to u, is 2 dx. Okay, so by the way, this is a very many chain rule. I keep saying chain rule. U substitution, because 2x is the only part that I don't like. If it was cosine x, it's very close to being good. This cosine x would be good. All right, so do I have a 2dx out here?
You have a 1/2.
The 1/2, or do I have a 2?
No.
No.
Just add a 2.
But we do exactly what we did last time. I can add a 2, I can make it 2dx, but I have to immediately cancel that out with the 1/2. So really, 1/2 times 2 is 1. Right? That doesn't change the expression. So I take the 2 to the right with the dx, and I take the 1/2 to the left. So I separate those numbers. Again, you can't do that with x terms, x or cosine x or something like that, but you can do it with numbers, a coefficient. Now I do a double substitution. By the way, this one, I'm just going to bring down at the end. Okay, so I'm just working this out now. So I have this 1/2 in blue, the integral. Then I have this 1/2. Here's substitution 1, cosine of u. So I replace 2x with u. And finally, right here, 2dx is equivalent to du. So if you're thinking, where did that 2 go? It's right there. It became du. The 2dx became du. What we've accomplished is it's now all in terms of the variable u, and we can just do an antiderivative. So any thoughts on you getting that spot though?
Okay.
Or better, I should say. Now what questions do we have? I bet you like that. Never mind. 1/2 times 1/2. Oh, I'm doing an antiderivative now. I'm sorry. Let's see. So I'm doing the antiderivative. So I'm going to write f of u. And let's see, 1/2 times, I can bring this 1/2 in there with that. 1/2 times 1/2 is 1/4. And then the antiderivative of cosine is sine. So sine of u. Plus c. I guess I don't need this, do I? I write that when we do FTC1. Okay, so last thing I did the antiderivative is just replacing u with whatever it was. So it's 1/4 of sine. U was 2x.
Is that the answer?
Well, yeah, I need to bring down this one. I drew an arrow. It was 1/2 actually.
Yeah.
Because that one we did separately a long time ago. We got that. Then I had to get the integral of the cosine of 2x. Yeah.
That was too difficult.
So I separated it with a trig identity, changed it to a trig identity, then I separated the sum there and did each one separately. The second part I needed, because it was cosine 2x, that's where I needed a little u substitution. And again, as soon as everything here is all in terms of u, do an antiderivative as normal. If you haven't got it in terms of u yet, all u, and you can't do that. Let's do another one. Anything else to add on that one? Next one, integral 4x square root of x minus 1 dx. Well, there is a composition, right? The square root part, the inside of that is my composition. X minus 1 is inside the square root. So I'm going to let u be the inside. You should always try that first. See if it works. So I let u be x minus 1. So du, the derivative, is dx. The derivative is 1 dx. So I just don't write the 1. What?
So we're good, right?
So we are good because dx is there. Okay. Well, let me start to write it. The only issue, so we'd have this, right? Square root of u. And in place of dx, we'd have du. But the problem is, right here, we still have an x term. And we can't integrate unless it's all in terms of u now.
So do we make a u2? What? A u squared?
No, good idea.
Okay.
You, at this point, normally you would say it didn't work. So you have to go back and choose a different u. But this one, it actually does work. So I need to get rid, so that 4 is going to be fine. I need to get rid of this x. Anybody see how we can get rid of the x? Circle that as the hint.
plus one.
I can solve for x, yeah.
Oh.
So now x is u plus 1. And I can replace x with u plus 1.
So you're gonna write, so then here. So when we add 1 to this, it would be u plus 1 equals x. So then what I'm gonna do is plug in u plus 1 in place of x. Okay, this it's kind of a cool question that it actually does work here. This is not too common. Like you might see from time to time. I know I put 1 on the practice like this, definitely. But I'm saying in general, you won't be able to solve. Like you won't be able to have this and solve for x and plug it in. It doesn't work a ton, but it does work a little. Okay, so now it's all in terms of u. Okay, I just need to simplify this, and then I'll be able to do an antiderivative. So first, I'm going to distribute that 4. So it's 4u plus 4. That's in parentheses. Times the square root of u, and we know to change that one to u, the half power. I'm going to, in order to do this, I need to, again, distribute the u to the half, and then it's going to work. So I'll have the integral of 4. Now this is really u to the first power. And so when I do u to the first times u to the 1/2, I'm adding exponents. I multiply with the same base. I'm adding exponents. 1 plus a half is 3 halves, 1.5. Plus on the next one, it's just 4u to the half. Okay, I write to u. I now do an antiderivative of each, and I'll be done.
So,
Well, I need to do the antiderivative now. So then, yes, but then that will be there now. So the integral, I can bring the 4 down. For u to the 3 halves, I'm going to add 1 with power rule. So it's u to the 5 halves over 5 halves. Bring the 4 down again. Here it's going to be u to the 3 halves over 3 halves. And plus c. Now, you know I don't like fraction and a fraction, so I'm going to change this one to times 2/5 and this one to times 2/3. Divided by a fraction, don't ask why, flip a second. Multiply. So the 2/5 times 4 will become 8/5. And I'm doing one last step here. The problem wanted it in terms of x. So I'm going to be replacing u with x, whatever u was to get it in terms of x. I can't find it. X minus 1, right? U was x minus 1. So I'm replacing u with x minus 1. And then I gotta simplify this one. 2 times 4 is 8/3. And then replacing u with x minus 1 plus c. Now, it's not a pretty one, but it worked. So we were able to find an antiderivative. So that's kind of, every single one we did was kind of a step up, just a little harder and a little more intricate things you could do. The only thing left I have to do now is what if there's actually numbers, if it's a definite integral. So we'll do a few of those in the back. Any thoughts on this one? Good. So last thing to do is what if we have a definite integral? It's still u substitution, but you have a change of variables, all right, for definite integral. So here's this was the normal rule on the last, well, 2 pages back of the reverse chain rule, the u substitution rule. It's integral from a to b. So what happens though is when you get your function just in terms of u, you also need your lower and upper limits of integration to be in terms of u. So you can see there it says u of a and u of b. Basically, the only change with this is whatever I called u, it's like back here, it's like u was x minus 1 here. I would plug in whatever these numbers are in for x and get new lower and upper limits in terms of the variable u. What else is about that? Yeah, because this really is, it's technically a u of x. It's a function based on x. Normally we just write u instead of u of x. Alright, so it's pretty simple. I'm just going to plug in the numbers, and then it's FTC1. So let's try one. First one, integral from 0 to 2. X squared squared of x cubed plus 1. Option 1, I kind of always like us to think about this first. Antiderivative straight up. No, don't know it. So, option 2, try u substitution. There's a composition with the x cubed plus 1 and square root. So I'll let u be the inside part. Okay, now I do the derivative du to see if this is on the outside. Derivative of x cubed plus 1 is 3x squared. 3x. Good. There's an x squared and a dx, right? But there's no 3. But that's okay. We can manufacture one by putting in a 3 here and then immediately canceling that out with the 1/3. Okay, only can do that for numbers, coefficients. So now we're good. We do have the derivative. 3x squared dx is on the outside, and so it'll work. Okay, so do this. Put the integral symbol. Don't put 0 to 2 yet. I need this 1/3. That just was part of it. But then this one, I'll put it. This 3x squared in dx was right here. So I'm replacing that one with du. Okay, so this 1/3 I needed. This 3x squared dx, that became du. And then right here, I just have square root of u. Because I put in x cubed plus 1 for u. Okay, now it's all in terms of u. The only issue though is I need new lower and upper limits of integration. All you do is you go back to the u. And I'm just going to do u of 0 and what was that, 2? U of 0 and u of 2. So that means is plugging in 0 and 2 into this function for x. Seeing what I get. So I put in 0. 0 cubed is 0. Plus 1 is 1. U of 2. So I'm plugging in 2 now. 2 cubed is 8. Plus 1 is 9. And so what that tells me is instead of 0, it's 1. And instead of 2 here, it's 9. Okay. Now everything is the same. So the first part I did was the u substitution. That's the only new part there, is getting different a and b there. So 0 to 2 was in terms of the variable x, 1 to 9 is in terms of the variable u. All right, FTC1. Any thoughts before I do that, though? Okay, I'm just going to write FTC1 here. So now I am doing an antiderivative. Well, here, it's really u to the 1/2. So the antiderivative, I got to bring down the 1/3. And then here I'm doing an antiderivative of u to the 1/2, which is u to the 3/2 over 3/2. No c, because it's a definite integral. I'm going to go ahead and change dividing by a fraction, same as multiplying by the reciprocal, 2/3. And so a better antiderivative will be 1 times 2, 2, 3 times 3, 9. 2 9s u to 3/2. That's a u. Okay, last step, f of b minus f of a. So this will be f of 9 minus f of 1. All right, so when I plug in 9 here, I'll get 2 9s and then 9 to the 3/2. I mean, you can just use your calculator. Just doing it in my mind. It's 27. 1 and 3, yeah, it's 27. So we'll get 2 over 1. So we'll get 2 times 27, 54 over 9. Minus, when I plug in 1, 1 to the 3/2 is just 1 to any power is just 1.
1 times 2 nines is 2 nines. So I subtract those, you can get 52 nines. So again, use substitution, change the variables to 1 and 9. Did an antiderivative, plugged in 9 and 1, and subtracted. Okay, now I want to show you one other thing, and see if there's any questions on this one. Guys, right here, here's an alternate. I didn't want to tell you this first, because I like to change a variable method. But watch this. Right here, I could change it back. So it's in terms of x. So, okay, u was x cubed plus 1. Okay, so I could change it back to this. Okay, all I did was put back in where u was. Then, if you wanted, you could do, this is capital A, you could do f of 2 and 0, the original A and B. You would still get that. I don't care which one you do. I prefer, and I'm going to show you this one where you change A and B. It's kind of just all in one thing. You don't have to do the substitution. But if you'd like, feel free to take away u, put back in what it was, and then use the original numbers. 0 and 2. Okay, anything else I can answer on part A? Excellent. Well, let's finish it up with part B and C here. So on part B, we're from -1 to 1. Function is 5r over 4 plus r squared. There's also another squared here. It's not on my board. Let's see. So no idea, right, what antiderivative is. That's option 1. Option 2, use substitution. So help me out. What do you think u should be?
4 plus r squared.
The composition, inside of the composition, yeah. Because the composition was something squared, and then the inside was the 4 plus r squared. Very nice. Now, du, the derivative, so it would be 2r, dr is the variable r this time. 2r dr. Okay, do we have a 2r dr up here?
We have an r.
We have an r dr, and we can, it's 5, so that isn't great, but we can get a 2, and then we'll incorporate the 5 as well. But right, we can manufacture a 2, that's what we want, and then immediately cancel it out with a 1/2. Okay, now it'll work. So let me go here and finish it. Okay, so I got that 1/2. Now I'm going to put the integral symbol. Don't do the numbers yet. Let's see, the 2, let's see if I can help this. The 2r dr right there becomes du. Alright, so I'm still going to have that 5 up top. But the 2r dr is gone. It's just du. Substituting. The 5 is still there up top, over, and then on bottom I'm putting in u for 4 plus r squared. So on bottom it's going to be u squared. Then I'm going to put in these numbers, yeah, and then I'll just do an antiderivative, and we'll be good. So the function is here, 4 plus r squared. So I need to do, I need to plug in -1 and 1. Let's start with +1. So when I put in 1 here, 1 squared is 1 plus 4 is 5. What about -1?
The same thing.
Same, -1 squared is +1 plus 4 is 5.
Why don't we get to 0?
Now before I even do the antiderivative, yeah, what's an integral using one of our properties from 5 to 5? It's like, it's 0. 0 property. 0 property. So this one, all of this is going to be 0. We got the 1/2 to bring down, which is still going to make it 1/2 times 0, which is 0. That's the property from A to A. The area under the curve of a point is 0. Nice how that one works out. Now guess what, guys? If you did the antiderivative here, you have to write it as 5u the -2 power, do the power rule. It would work. You still get 0. But might as well. might as well change it there. Okay, that was nice how it works out. Let's do the last one. Anything I can answer though, part B? Okay, last one. So I've got an integral from pi over 4 to pi over 2, cotangent x times cosecant squared x. Temporarily write what this means. Really, it's cosecant of x squared. So our natural choice for so first of all, I don't know the antiderivative of this whole thing, but natural choice for u substitution would be the inside, cosecant. Okay, warning, it's not going to work, so if you want to write it down, great. If not, just go on. So if I let u be cosecant x, du would be the derivative. Derivative of cosecant is negative cosecant cotangent. Right. Oh, wait, we just said we have cotangent.
Yeah.
So if we used u, the u squared, we have cotangent, we don't have cosecant. So it didn't work. Because we can't manufacture our own cosecant. We can do a number, but not cosecant. So that didn't work. We must go back and choose a different u. And I guess you go back and choose a different u. And actually, this is one where it's not the composition. That's why this one's a little harder to see. You should go to the composition part first. But actually this one, watch what happens if we just let u be the cotangent. Du is the derivative of cotangent, which is what? Negative. Because tangent is positive secant squared, cotangent is negative cosecant squared x.
Add a negative sign?
And that's all we're going to do is add a negative sign because we got cosecant squared x. We just need a negative. So we need this negative up here. So I'm going to throw in a negative, but I immediately have to cancel it out on the outside. It's really -1. Okay, so let me write the final. Bringing this negative down. Integral, don't write the a and b yet. Let's see, so, okay, u is cotangent. And then we have, well, I made a negative there. We have negative cosecant squared x dx. I guess I go back to this one. We have negative cosecant squared x dx. And so it's just du. This one actually breaks down. It looks like it breaks down a pretty simple integral, just u. The only thing that changes that negative. Okay, I'm going to change the pi over 4 and pi over 2. So it's in terms of u. So I just need to plug in into my u function. I need to plug in pi over 4 and pi over 2. So move it up here. So I do cotangent of pi over 4. I like to think of tangent of pi over 4, which is what? 1. Cotangent is the reciprocal, which is also 1. And so that one goes there. Then I need cotangent of pi over 2. And right here, so this one, cotangent is cosine over sine. And this point is 0, 1. So cosine over sine is 0 over 1, which is 0. Or you can do tangent, which is 1 over 0, undefined. Reciprocal of undefined is 0.
What's upside down?
Okay, so that's what we get, negative, and then the integral from 1 to 0. Now, you could do it as is, leave the negative out front. Or, I already heard somebody at this, is that backwards, 1 to 0? You read bottom to top here, 1 to 0. Well, we can change it, right? Change the order. And if we do, we change this to a positive. See, I've made it even easier now. So that was the order property. Sorry, order property. Okay. And finally, it's just an antiderivative of u, and we'll plug in 1 and 0. So the antiderivative of u is power rule. This is the first power. So it'll be u squared over 2. So now I'm going to do f of 1 minus f of 0. Plugging in 1 here, 1 squared over 2, that'll just be 1 over 2. minus plugging in 0 would be 0 over 2, which is 0.